GitHub gives you 5,000 API calls every hour. Call number 5001 and you get a 429. Simple. Except GitHub doesn't run on one server. It runs on thousands of them, spread across data centers around the world. And during peak traffic, dozens of those machines might be processing your requests at exactly the same moment, each one holding its own little piece of the truth. So here's the real question. How do thousands of independent servers agree on a single number? Because the obvious answer breaks. It breaks silently, it breaks at scale, and it breaks at the exact moment traffic is highest and you can least afford it. By the end of this video, you'll understand the bug, the fix that production systems actually ship, and the trade-off hiding underneath all of it. Before we fix it, let's be clear about why rate limiting exists at all. It exists to protect your systems, and it protects them in 3 different ways. First, your infrastructure. One buggy client stuck in a retry loop can hammer your API thousands of times a second and flatten it for everyone else. A rate limiter is the circuit breaker that keeps one bad actor from taking down the whole service. Second, fairness between users. One customer scraping at full speed should never make everybody else's requests slower. The limiter carves the capacity into fair shares, so a single heavy user can't starve the quiet ones. Third, cost. Every request you serve burns real money. CPU cycles, network bandwidth, database queries, they all add up, and an unbounded API is an unbounded bill. So you publish a contract, maybe 100 requests per minute, maybe 5,000 per hour. Choosing that number is the easy part. The hard part is enforcing the promise when no single server ever sees all of the traffic. On one machine, rate limiting is boring. You keep a counter for each user, you increment it on every request, and you reject anything above the limit. When the minute rolls over, you reset the counter to 0. Done. This is called a fixed window, and it works right up until you hit your first edge case. Suppose we allow 100 requests per minute. A user fires 100 requests at 12:01:58. The counter hits 100, every request passes, and a second later the clock ticks over to a new minute. The counter resets to 0. So they fire 100 more at 12:02:04. The counter climbs from 0 again, and all of those pass too. 200 requests in about 2 seconds, and every single one was allowed. You promised 100 a minute. You just served double. And nobody was even attacking you. Real traffic is naturally bursty, and a burst that happens to straddle the boundary between 2 windows gets counted as 2 separate minutes. The window resets at exactly the wrong moment, and your clean little counter quietly leaks. Engineers solved this years ago, and there are 2 algorithms worth knowing. The first is the sliding window log. Instead of resetting a counter on minute boundaries, you record the timestamp of every request, and you count how many fell inside the last 60 seconds, measured continuously from right now. As time moves forward, old timestamps drop off the back of the window. There's no boundary to straddle, because the window is always 60 seconds wide and always moving. The burst that fooled the fixed window now gets counted as what it actually is. The second, and the one most large systems reach for, is the token bucket. Picture a bucket that holds tokens. Every request takes 1 token out. If the bucket is empty, the request is rejected. And tokens drip back in at a steady rate over time. This gives you 2 knobs to turn. The refill rate sets your long-term average throughput, say 100 tokens per second. The bucket size sets how big a burst you'll tolerate before you start saying no. That second knob matters more than people expect, because real traffic is never smooth. A single page load might fire 20 API calls at once. Mobile apps reconnect in waves. Browsers retry. Users refresh. Traffic arrives in spikes, and a full bucket absorbs the spike while the refill rate quietly holds the long-term average in check. So the math is solved. 2 good algorithms, well understood. This sounds like the whole story. The hard problem here was always coordination, not arithmetic. Here's where it gets interesting. Imagine 20 API gateways sitting behind a load balancer. A request comes in, the load balancer picks a machine, and it does that using a hash of something stable, often the client's API key, so the same client tends to land on a predictable set of servers. But the key insight is that any given user's requests can be spread across many of those gateways. There is no single machine that sees everything one customer is doing. Now suppose each gateway keeps its own token bucket in local memory. It's fast, it's simple, and it's completely wrong. You thought you were enforcing 100 requests, but every server independently allows 100. So your customer isn't dealing with 1 limiter, they're dealing with 20. Your 100 request limit quietly turned into 2,000. And the scary part is you won't catch it in any one server's logs, because each gateway is doing its job perfectly. It just can't see the others. The obvious fix is to stop keeping the state locally. Pull it out into one shared place that every gateway can reach. Put the counter in Redis, a fast in-memory data store, and now all 20 gateways read and write the same number. Problem solved, except not really. Watch what happens when two gateways serve a request at the same instant and the bucket has exactly one token left. Gateway A reads the counter from Redis. 99 used, 1 remaining. Plenty of room. A fraction of a millisecond later, before A has written anything back, Gateway B reads the exact same counter. It also sees 99 used, 1 remaining. It also thinks there's room. Both gateways check the limit. Both decide to allow the request. Both increment, and both write 100 back to Redis. 1 token, 2 requests served. The counter says 100, but 101 requests got through, and the extra one vanished into the gap between the read and the write. This is a race condition, and here's the cruel part. The more traffic you have, the more often 2 requests collide on that last token, so the leak grows in direct proportion to load. It is smallest when you don't need protection, and largest at the exact peak when you need it most. The moment your system is under real pressure is the moment your protection starts quietly failing. The real mistake was separating the read from the write. Redis itself was fine. In a distributed system, anytime 2 operations can interleave, anything that happens between them can go wrong, and that gap is where the race lives. The fix is to collapse the check and the update into a single operation that cannot be split. Redis runs on a single thread and executes Lua scripts atomically. While a script runs, nothing else touches that data, so the whole thing happens as one indivisible step with no gap for a second gateway to slip into. So you push the entire decision into one script, read the current token count, refill it based on how much time has elapsed since the last request. If at least 1 token is available, subtract 1 and allow. Otherwise, reject. Then, write the new value back, all of it, atomically, in 1 round trip. Now when 20 gateways hit Redis at once, the single thread serializes them. They line up and run one after another against one source of truth. Gateway A takes the last token and writes 99 remaining. Gateway B runs next, sees 0, and correctly rejects. No race, no leak. The bucket now behaves exactly as if there were only 1 server enforcing the limit, because logically there is 20 machines, but 1 place where the decision actually gets made. We fixed correctness, but we bought a new problem. Every single request now makes a network round trip to Redis before it can be answered. 1 millisecond per call sounds harmless, until you're handling hundreds of thousands of requests per second. Now Redis sits directly in the critical path of every request, and your P99 latency climbs with the load. Worse, that single Redis node becomes a bottleneck and a single point of failure. Everything funnels through it. So large systems add another layer, a hierarchy. Redis still owns the master quota, the real global limit. But instead of asking it about every request, each gateway leases a small batch of tokens up front. If the global limit is 1,000 per second across 20 gateways, each one grabs a local allowance of, say, 50 tokens and serves them straight from memory. Most requests are now decided locally, in nanoseconds, with no network call at all. Only when a gateway burns through its lease does it go back to Redis to ask for more. The chatter with the central store drops by orders of magnitude. The result is dramatically lower latency, far less network traffic, and much higher throughput. But there's a catch. Because each gateway holds a small private reserve, the global count can briefly drift and you might allow a few more requests than the contract strictly promised during a burst. You trade a little bit of accuracy for an enormous amount of performance. And that is what real engineering looks like. You decide, on purpose, which imperfections you can live with. Eventually something fails. Redis crashes, the network partitions, or the whole cache simply becomes unreachable. In a distributed system, that's a certainty you plan around. So you have to decide in advance what your limiter does when its brain goes dark. You have 2 choices. The first is to fail closed. If you can't reach Redis, you reject everything, because you can't prove a request is under the limit. That keeps the limit safe, but it means a Redis outage instantly becomes a full outage of your API. Your rate limiter, the thing meant to protect you, just took you down. The second is to fail open. If Redis is unreachable, you let requests through anyway, maybe falling back to a rough local limit. Your protection is gone for those few seconds, but the service keeps serving. Most production systems choose to fail open, because degraded protection is almost always better than a total outage. A brief window where a few extra requests slip through is survivable. An API that returns nothing to anyone usually is not. And that's the real lesson. In distributed systems, you design for failure from the very start. You don't ask whether a component will fail. You assume it will, and you decide ahead of time exactly how the system should behave when it does. So the next time an API answers you with a 429, remember that behind that one tiny status code is far more than a counter. There's a token bucket smoothing out your bursts. There's an atomic script serializing 1,000 concurrent decisions. There's a hierarchy trading a sliver of accuracy for speed. There are explicit failure modes, chosen on purpose. And there are thousands of separate machines straining to behave like a single one. Engineers solved the counting part decades ago. The interesting part of rate limiting lies somewhere else entirely. The hard part is agreement. Agreement on the shared state, agreement on the timing, agreement on who, out of 1,000 racing requests, gets the very last token. Every 429 you've ever received is quiet proof that somewhere, a group of independent machines managed to agree in a few milliseconds to tell you no. If this is the kind of systems thinking you enjoy, the kind where the simple answer is wrong and the real answer is a trade-off, then like this video and subscribe. That's exactly what this channel is about. I'll see you in the next one.